I think we're ready to start.
Yeah, we can start.
So hey everyone, thanks for tuning in. So I'll be presenting a particular paper on macroscopic superpositions, and I just want to draw your attention to the Dora Hacker Dojo page. Dora Dōjō is an open source community focused on upcoming technologies such as encryption, Web3, and also foundational quantum mechanics. And Dora Dōjō organizes these knowledge sharing sessions, one of which is happening right now in the form of live broadcasts, audio, and also text, which is published in the Dora Dōjō Hacks forum. And there are a variety of topics such as L1 and L2 consensus algorithms, blockchain architecture, and related content that is published on GitHub. And some topics are, for example, Scroll, zero knowledge proofs, Starkware, optimism, public key encryption, and so on. And yeah, there's also some parts on quantum computing, quantum information, and that's the direction that the live workshop will take today. So this is the page, and you can look at all the bounties that you can get for presenting certain results. For example, there's some stuff on measurement, various quantum computing architectures, such as measurement-based, neutral atom, or superconducting. And I will start off by presenting a result from a paper from 2017 from Skotionis, Dürr, and Sikatsi. And in this particular paper, the authors show that the size of a classical reference frame required to certify a quantum state to reliably distinguish between a superposition and an incoherent statistical mixture requires a measurement device that is quadratically bigger than the superposition state. And this imposes practical constraints on what sort of states you could actually measure and what sort of quantum states in particular you could distinguish from their classical counterparts. So we'll start off the workshop just by looking at the differences between coherent superpositions and statistical mixtures. This is sort of part of any introductory quantum mechanics course, but I think this is extremely important and lies at the heart of the derivation. So we'll just start off with a really general introduction to this topic and consider a very simple example just to start off with. So if we have a two-dimensional Hilbert space where a Hilbert space is a mathematical formalism for describing any sort of quantum system, and we consider a Hilbert space spanned by two qubit states L and R. So we have as our two vectors which define a two-dimensional vector space. L and R could be, for example, two polarization states of light, for example, left and circularly polarized. And the important thing is that they're orthogonal. So if I take the dual of L or the dual of R and multiply it with L or R, then this would equal 0. And yeah, because these basis states are normalized and orthogonal. And I think a simple example of a particular coherent superposition state would just be a bipartite superposition of L and R, which is equally weighted. So we could, as our simplest example, just consider a following state. We could just consider an equally weighted superposition of L and R. Where before making any sort of measurement, this is a particular state which has not a well-defined polarization of L and R, but is in a coherent superposition. Thus, while the state retains its coherence, i.e. its quantum properties, it does not have a uniquely defined polarization in this particular LR basis. So what happens if we make a measurement on this particular state? Upon making a measurement, the state would decohere, i.e. lose its quantum properties and its coherence, and we would observe either this polarization or this polarization. And this is somewhat counterintuitive because you would assume that like the information captured in this particular state does not represent any particular polarization, but upon making a measurement, we only observe one of these outcomes, either L or R. And this is also in philosophy of physics, sometimes called the measurement problem. And a lot of people have written a lot about this in the past decades. Moreover, just by looking at this example, I want to reiterate that the absolute value squared of the coefficients of either of these vectors gives you the probability of measuring either of these outcomes if you perform some sort of measurement. Moreover, this is a pure state, which is important when we compare this to a mixed state. And in particular, the state is pure such that when we consider its density operator, which is equal to het and the bra of this particular basis vector, then this is a pure state because the trace of rho squared, which is the sum of the diagonal elements, is equal to 1. And this is a necessary and sufficient condition for this to be a pure state. Now, if we compare this to mixed states are not pure because they don't satisfy these conditions. And if we consider mixed states, they actually cannot be expressed as a single ket. So if I write down a classical mixture of L and I, then this would look like this. And this is the density operator representation of a particular mixed state. Now, if I perform a measurement on the mixed state, my measurement statistics would actually be exactly the same as for the pure state. So if I perform a measurement in the LR basis, the only thing I would observe would either be an L outcome or an R outcome. And again, this is a bit paradoxical because this is fundamentally different from the pure state that we described before. So the density operator of the pure state is not equal to the density operator of this mixed state. And the coherence between the two states we looked at previously in equation 1 wouldn't be captured by measurement in the LR basis because you would assume from the measurement statistics that these two are equivalent, even though they are mathematically distinct. However, we could switch our measurement basis and we can resolve this paradox. So if we measure in the plus minus basis, where plus minus is equal to the superposition of the two basis elements LR with either a pi or a zero phase between them, then we would observe fundamentally different measurement outcomes. For example, the former would always lead to the outcome plus. So if we have this state and we measure it, it would always be plus. And if we measure this state, then it would give you equiprobable measurement outcomes of plus and minus. Plus is 50% probability, or minus is 50% probability. And if you want a more comprehensive introduction, I would refer you to a book called Quantum Communication, Computational Information by Nielsen Chang, which gives you a much broader introduction to this topic. But all that's required for what follows is the ability to distinguish between a pure state, which is represented in equation 1, and a statistical mixture expressed in equation 2. So what particular states are we considering, and what particular states do we want to distinguish? What particular coherence superpositions do we want to distinguish from the respective statistical mixtures? So the authors consider 3 types of coherence superpositions. So we are interested in macroscopic superpositions. So the two states must be macroscopically distinct, which means that the difference between the eigenvalues is large. And we can consider three types of two-component superposition states. We can consider states of total photon number or energy. So here, 0 and n are single mode Fock states. There are eigenstates of the photon number operator with eigenvalue 0 n. This means that the first ket represents a particular state with no photons, and this particular ket represents a state with n photons. And then this is a coherent superposition of a 0 and an n photon state. Moreover, we can also consider spins. So we can also consider a superposition of n spin-ups and n spin-downs. The reason why we can't consider just a superposition of two spins is because this wouldn't really count as a macroscopic superposition. So this is a tensor product here, which simply means that in this particular state, we would consider this to be sort of n spin-ups. So this would be like the first spin, this would be the second spin, so on until we get to n, and the same holds for the other state, which is a representation of n spin downs. And they also have eigenvalues plus minus and a half, and this is a THZ state. Moreover, we can consider delocalized objects. So here we have a state which is in a superposition of position eigenstates. So here the L has nothing to do with the polarization example I mentioned previously. We just have a superposition of position eigenstates. So X here is the position operator for a particle of mass m, and the eigenvalues are the actual positions that these particular states represent. And we can think of this, for example, as a quasi-particle describing the center of mass of a composite system. And these states need not even be eigenstates for the position operator, but they could also be Gaussian wave packets, for example, in a potential well, if you consider atomic lattices. And for our purposes, the important thing is that the width of this wave packet is ignored as long as it's much smaller than the separation of the two states. So long as the distance between the states is much larger than the width of the wave packet itself, we can consider them to be macroscopic because they're extremely far from each other. And we would, for example, consider like some sort of wave function which has width L and then they are separated. So this is this is the distance L between them, and this is the width of this particular wave packet, and then L will be much larger than the width, and then we consider these to be macroscopic. Moreover, the author importantly generalized this to just general macroscopic quantum superpositions. So we don't need to only consider these two component states, but we could also just consider any sort of generalized superposition, which is can just be expressed as a generalized sum of coefficients phi n and kets n, where n could represent anything such as eigenstates of photon number, spin, position, or anything else that you could possibly think of. And the important thing here is that they must also exhibit these macroscopic quantum coherences. So if we, for example, consider the coherence between, so this would be the coherence between kets n and bra m, and this would have particular coefficients, then these components are are distant, which implies that there is a large difference between n and m. So this would imply that if this is around n, and we consider n to be particularly large, then the variance of phi n must be large as well. And the particular state we just describe in this particular equation, this generalized superposition state, must be distinct from a sort of semi-classical state, which contains coherences for kets which are not separated by large n, yet none for these n and m's which are far from each other, or where the absolute value of the difference between n and m is extremely large. And this would imply that if you can't distinguish between the sort of semi-classical state with no macroscopic coherences to this particular state, which is a quantum state which exhibits macroscopic coherences, then we cannot detect coherences in the scale larger than n beta, where this is just a sort of an arbitrary scale which is introduced to describe what is macroscopic and what is not. And yeah, there are a variety of measures which determine whether a particular quantum state is macroscopic. And I think, yeah, I just want to emphasize the notion of faraway coherences because it crops up again in the later derivations. And yeah, there are various other references that interested listeners can tune into after the talk. I also want to give sort of a quick just background of the state of the art in terms of experimental demonstrations. So demonstrations of microscopic superpositions are ubiquitous in experimental quantum physics. The entanglement of spatially separated photons led to the Nobel Prize in 2022, and experiments with electrons, neutrons, atoms, molecules, and so on have been performed to create and detect coherent superpositions. Macroscopic superpositions, such as the famous Schrödinger's cat thought experiment, which is postulated to exist in a superposition of being dead and alive at the same time, have had sort of played an important role in the historical development of quantum mechanics. And in general, nothing precludes you to apply quantum mechanics to an extremely large length scale or larger and larger systems. But practically and technically, no one has been able to really perform any experiments with cats and superimposing them into dead and alive states, because in general, T-coherence is an extremely large problem, and it's extremely hard to maintain coherence in macroscopic systems of any reasonable timescale, such that you can perform an experiment and actually detect this particular coherence, because they're very hard to isolate from the environment and will interact with all sorts of things in the environment. And I guess some progress has been made, though, in exhibiting quantum behavior on larger scales. For example, recently there's a paper which demonstrates the entanglement of a tardigrade, which is a sort of similar to like a small biological bacteria with a superconducting qubit, or the entanglement of quantum optomechanical systems. And yeah, again, there's some references there if some listeners are particularly interested and want to go a bit further. So going into a bit more detail now on how one actually gets to this derivation, which constrains the size of measurement devices required to measure macroscopic superpositions. And the first is, I think, to understand what the task is at hand. So as I mentioned previously, what we need to be able to do is just discriminate between a coherent superposition and an incoherent mixture. So if you think back to these two states that I outlined right at the beginning, which are a superposition of L and R and a statistical mixture of L and R, then we need to be able to perform a measurement which distinguishes one from the other. And the states we're considering now are, I think, firstly, you should consider these three states. So we either have a macroscopic superposition of photon number, we have a superposition of total spin, or we have a superposition of position. And the goal is to relate the size of the superposition to the size of the measuring device required to distinguish this superposition from its corresponding incoherent mixture. And practically speaking, an experimentalist is given a particular physical system in either of these configurations. It could be in the statistical mixture or in a coherent superposition. And the prior probabilities of preparing the state and the actual experimental state in either is equal. And then there's a particular measure which is important for determining the probability of success, which is the trace distance of the two states. So the trace distance T is the latter part of this equation, which describes so notation is usually 2 lines. This is the coherent superposition. This is the statistical mixture. And the trace distance also, I've detailed this in the appendix, is trace distance AB, where A and B are particular matrices. So we have a representation in a particular basis. So this is equal to, if this is row soup, this is row mix, then this would be equal to row soup minus row mix, Hermitian conjugate minus row soup minus row mix. And this is a calculation which becomes important again, so I was going to go into a bit more detail just to make sure everyone can follow. And then the success probability is given by 1/2 times 1 plus t, where t is equal to the trace distance between those two states. And this can, of course, be increased if you prepare several identical copies and repeat the measurement n times. And there's an implicit assumption there that the reference frame used to perform this measurement doesn't change or doesn't degrade if you perform several measurements one after the other. And one can also use the quantum Chernoff bound to relate the trace distance to the maximal error probability if in the limit of n copies being prepared. And this is a slightly involved mathematical derivation, which I'm not going to go through in the interest of time, but this just relates the number of measurements to the maximal error probability, and you can see there that p error as a function of n, where n is the number of measurements that you perform, is approximately smaller or equal to 1 minus t squared to the power of n over 2, where t is the trace distance. So you can see here that if you want to minimize the error probability, it would be advantageous to make this expression as small as possible, and therefore a larger trace distance in general gives you a lower error probability, and likewise, the larger n is, the smaller the error becomes. The more measurements you perform, the smaller your error probability is. So yeah, that generally explains the task that we are faced with, which is distinguishing between coherent superpositions and incoherent mixtures. And I've introduced the concept of the trace distance, just as a very sort of general measure for distinguishing between particular states. Now I'll go on to something a little bit different. So I'll try and relate the what we sort of consider a measurement device to something that can be expressed in quantum mechanical terms. So the authors resort to basically describing all things that are associated with making a measurement in one single state RF, where RF can also be thought to act as a reference frame. So if you want to detect any sort of coherence, then you need some sort of reference with respect to which this coherence will be detected. And this sort of encaptures the notion of a measurement device. And this is perhaps a bit strange, but I think the way to think about it is that if you are an experimentalist in a lab, then everything about you, the observations you make, and everything, all the apparatus you have in your lab, be it, I don't know, a beam splitter, a photodetector, or anything, will just be described in this state RF. And in particular, you can then kind of narrow down what RF actually represents if you consider different sort of measurement tasks that we'll look at more closely in relation to the 3 different types of superpositions that we've outlined before, which are photon number, spin, and position. So the reference frame state encodes all relevant information about the measurement device. and the state will also play the role of a measurement device in what follows. And the simplest example is a coherent state serving as a reference frame. In particular, this is then a reference frame for a phase relative to which a quantum operation can be performed, for example, on the state of an atom. So you can, for example, also consider an atom being in a superposition of two of its ground states, and then you want to measure the phase of this this particular superposition state, and want to sort of measure its coherence to certify that this is a coherent superposition. And then you need some sort of phase reference, which could be a coherent state. So coherent state is usually represented like this. And again, I've outlined this slightly more carefully. In general, you just describe a Glauber coherent state in the Fock basis. So if you want this to be normalized, and this is a superposition of various photon number states, where alpha basically determines the weighting of each of the individual contributions of the individual Fock states in the superposition. So n represents Fock states. So 0 would be no photon, 1 would be 1 photon, 2 photons, and so on. And yeah, this is a particular example of a state which would serve as a phase reference. And moreover, there's unitary interaction between the states of the system and global reference frame state RF, which allows for a particular phenomenon measurement in the basis K, such that the probability is given by this particular expression where TR represents the trace. So we consider our kind of composite system of whatever quantum state we want to measure in the first place, and then also consider the entire experimental apparatus used for performing this measurement. So the state would actually look like this. This would be, I don't know, superposition of photon number, spin, or position. And then the rest of the system is described by this kind of map of this state RF, which is your reference frame. And then, so this is total system, where again, this is a tensor product of these two. And then as you can see here, you would perform some sort of unitary interaction between the state and the reference frame state. And then K is just your basis. So K for photon number would, for example, be, you want to measure the 0 photon state. And we can treat this whole system as a closed system. And so this is just the probability of observing the state K, where K is just representing a generalized measurement outcome, whatever sort of superposition state is prepared in the first place. And this particular whole system must respect the symmetries of our physical laws. And these could, for instance, be the Galilean group, which encapsulates various space-time transformations, such as time translations, space translations, rotations, and boosts. I mean, you could also consider other groups, such as, I don't know, the Poincaré group, but in general, the Galilean group is kind of the most simple group of symmetries, which are respected by our physical laws. And this may seem strange at this point, but the reason this is important is that measurements are invariant under symmetry transformations. And in what follows, these transformations will be used to make particularly nice simplifications of the probabilities of distinguishing between coherent superposition and a statistical mixture. And these expressions are sort of, it's important to express these in simple forms such that we can relate the probability of success to the size of the quantum states themselves and also the size of the reference frame. Because that's kind of the aim of this whole presentation, is to rederive the result, which relates the size of a classical reference frame to the superposition state itself. And by using Noether's theorem, which is actually just a classical theorem, you can associate every symmetry of a system with a conservation law. And this means that the only interactions U can be performed. So U is a particular unitary interaction, which you can see acts on the whole system here, are those which commute with VG, where VG is a unitary representation of these particular symmetries, where, again, this is expressed rather formally because G is actually a generalized symmetry group. And the example of the Galilean group is used here, but this could in principle also be a different symmetry group. So as I've mentioned before, all the information required for a measurement is encoded in the generalized reference frame state RF. And this includes the observer's body, retina, and so on. And we can make similar sort of assertions about the possible types of measurements which could be performed. The measurements which are performed, so this is a projector operator value measurement, have to satisfy this particular equation. So they must also commute with a unitary representation of this group. And the projector K represents the observer's awareness of a particular measurement outcome. And again, this what K actually represents depends on the particular type of state that you want to measure. And the important thing here is that this is invariant under symmetries. So the probability of measuring this particular outcome K is actually invariant under a transformation G, where G is the G twirling map and applies a particular symmetry transformation to this total state. So you can see this is kind of a continuous variable transformation where VG is the unitary representation of this symmetry group, and it's applied for all the elements G of the group to the total quantum state plus reference frame state. And in these two equations, we can see that the symmetry restrictions on the operations and measurements mean that this particular configuration, where we've applied the G twirling map, which encodes the symmetries of whatever symmetry group we are considering, mean that the measurement outcome under the symmetry transformation is indistinguishable from this measurement outcome. We haven't applied any sort of, we haven't, for example, transferred this state in space, or rotated it, or transferred it in time. And yeah, this is really important for the derivation which follows, because it basically means that you want to use all the symmetry transformations that make the calculations more simple for determining the form of the trace distance t, which gives you an indication of how successful your measurement will be in distinguishing between the incoherent mixture and the coherent superposition. And yeah, in the absence of an external reference frame, this symmetry transform state is the one that one would is a state that one would ascribe to the total system plus device. Yeah. So now we'll take sort of a quick diversion where we're going to look at what the authors understand to be classical states. So measurement devices are incorporated into a quantum description of a joint system state through the quantum state RF. So this is the particular state that the authors have chosen, yet in general, we really understand a measurement device to be classical. And then there's a question of how this can be reconciled, because we have kind of considered a quantum description of RF. This is just a particular basis state of our quantum system. Yet, when we think of a measurement device, we think of a macroscopic device that can't really be described quantum mechanically. Usually, the things we describe quantum mechanically are kind of very microscopic in terms of this scale that we consider. So they're usually like single spins, electrons, photons, but they're not usually these large generalized representations of something, such as, for example, here, a total lab with experimentalists performing a measurement and all the devices used to make the measurement in the first place. And here I just quote the definition, which is stated by the authors of one, which is that states of any macroscopic quantum systems comprised of n constituent parts, as classical if their collective quantum effect, can be explained as the accumulation of n microscopic quantum effects. And this includes pointer states, generalized coherent states, and such states are known to be robust, fixed point of general local decoherence processes. So basically, the author considered the aggregation of a macroscopic, so they consider the accumulation of sort of order n microscopic quantum effects, and then describe a macroscopic quantum system as the kind of accumulation of these n constituent parts, which each exhibit microscopic quantum effects, and that's when they are classical. And yeah, there's also some more kind of technical details on any sort of local noise that acts on this and how this particular state would decohere. And I think one more important thing is that the scaling of the average variance. So the authors also show that after the action of generic local noise, any state can be decomposed as a mixture of pure states with the average variance of any extensive quantity that only scales linearly with a number of subsystems. And in what follows, we will consider various types of classical measuring devices, for example, coherent states of light, spin coherent states, or products of localized wave packets corresponding to classical measuring devices for energy, angular momentum, and position, respectively. One can also extend the results to general states without an explicit formulation of RF, such as the just super generalized formulation of any sort of macroscopic superposition here. And and all that is required is an understanding of the scaling of the variance with respect to its size. So we'll start off by trying to rederive or basically go through the result presented in the paper, where we consider a superposition of photon number. So we start off with a generalized superposition of photon number, and the states we need to distinguish are a so we have coherent superposition of zero photons and n photons, and we have an incoherent mixture of with a zero photon contribution and n photon contribution. And we need to distinguish between these two. And what we want to, sort of the point of this derivation is that we want to relate the required size of our measurement device to the size of this particular macroscopic superposition. I'll say again that in the absence of a phase reference, we can't actually make this distinction because there's no phase invariant measurement capable of distinguishing between the two states. If we just measure in the 0n basis, we obtain equivalent measurement statistics, and there'd be no way of distinguishing between either this or this particular state. So if we want to have any chance of distinguishing between the two, then we need some sort of phase reference. And here I'll come back to one thing I described before. So a classical measurement device is best described by coherent state or of RF with alpha squared photons in total. So we consider our FCAT to be described by a coherent state. And then we apply this G twirling map, which encapsulates the particular symmetries under which our physical laws are invariant to a global state. And this does not change probability of making a particular measurement outcome because in this particular symmetry, we'd be averaging of all possible values of theta. And this is because when we apply the map G, where VG is the unitary representation of this group, this is in this kind of continuous representation, we would consider the under the angle theta rotational invariance of this. And when we apply this, all the coherences between the states with different photon number, where K is just the total photon number of the system and the reference frame, actually vanish. So we have a mixture, or as you can see in the plus here, this is a direct sum of states with fixed total photon number. So there can't be any coherences with states with different photon number. So for example, you couldn't have a coherence between if you had 0 photons in your system, and then you had 1 photon in your reference frame, and you had you wanted to observe the coherence between 0 photons in your system and 3 photons in your reference frame, then this will just be 0, because G twirling map, which basically encapsulates the symmetries that are relevant, or that make the kind of calculations easier, erase all those particular coherences. So yeah, once we apply G to rho, where rho is just the generalized density matrix representation of an unknown state, which is either this coherent superposition or this incoherent statistical mixture. And yeah, when you apply the G twirling map, then this is the representation of this particular state, where this gives you a sum of all the states, where, as you can see, this is the reference frame with n photons, and this is the system with k minus n photons. So the total number of photons is always conserved. And now that we've made this this particular simplification, so we applied G. So this is a G twirling map which calculates all the symmetries, and you apply this to and this becomes a direct sum. And the sum is over k. K goes from 0 to infinity, and k gives you a particular block of total photon number. And this is and then sigma k, as I said before, just gives you a sum of all fixed photon number states. So this is just a projection into blocks where there are fixed total photon number between both the RF state, between the RF reference frame and the system. Now for k smaller than n, this state qk rho k for both the macroscopic superpositions and the mixture reads the same. However, for a k much larger than n, one gets this particular representation. So this would be the coherent superposition. And you can see that in this particular basis representation, the coherent superposition has these off-diagonal elements, which represent the presence of coherence. And here you can see the incoherent mixture has no off-diagonal elements. And this is a particularly nice and kind of simple representation of this. And that's because we considered particular symmetries, which then erase coherences between states with different total photon numbers. Otherwise, the calculation would have been significantly more complicated. So here we have the basis of k photons in the RF state and 0 photons in the system, and k minus n photons in the RF state and n photons in the system. So again, the number of photons in either of these basis states is the same. And the important thing is that if we consider a particular representation in this basis of either the coherent superposition or the incoherent statistical mixture, then they have fundamentally different. So we consider this kind of projection into these fixed photon number sectors. And this is equal to 1/2 times UK minus n. Minus n. And then if you consider kind of the same thing, but you replace with this, where this is the incoherent statistical mixture, then the basis representation becomes, you see that, becomes one which has no off-diagonal terms. Is this particular basis representation has no off-diagonal elements, we can simply calculate the trace distance, and that gives us an expression for t. So if you think back to trace distance, which is if you consider the actual kind of difference between these two density operators, then we can see, because this would be a sum over all n. So you start off with k is equal to n, and you go to infinity. And the trace distance in this particular representation is extremely easy to calculate, which is not the case for these generalized states where you haven't erased all occurrences between states with different total photon numbers. There, this calculation would be extremely difficult. The trace distance between these two, so we consider this and this. So I'm not going to actually go through the calculation, but just think back to trace distance a minus b. So it's a minus b Hermitian conjugate times a minus b, and then you consider this to be a and this to be b. So we subtract these two matrices from each other, consider the Hermitian conjugate, and then multiply it by the difference. And what we get, take then the absolute value. So we get the square root of this product. then what you get is a, so obviously the factor of half carries through, so T of a, E, I'll make a note where it says T of, so we can maybe consider this sigma S and sigma X, sigma S, sigma mix. Then this will actually be equal to the sum from K is equal to N to infinity times 1/2 root A minus N. And this is the particular off-diagonal element. And then this particular coherence can be expanded as an exponential. So we can consider this the limit of large alpha. So that's a very large coherent state with a lot of photons, and also large n, which means that the particular state we're trying to measure is in a superposition of no photons and an extremely large number of photons. So practically, you could consider, for example, a state superposition of 0 photons and, I don't know, 1 million photons, which would then be what we would consider a macroscopic superposition. And then you could expand the sum. So if I maybe these, you can expand the sum for large alpha, large n. The sum is equal to following exponential. And this is the particular regime we're interested in ultimately. And you can see that if you want a if you want t to be small, so this is equal to 1/2 1 over e to the n squared over 8 alpha squared. So you can see that if alpha is very small compared to n, this will completely blow up. Whereas if alpha is much bigger than, so if alpha is bigger than, much larger than n, then what you basically have is that this becomes the probability of successfully distinguishing the two becomes extremely large. So the probability of distinguishing between the coherent superposition of photons and the statistical mixture of photons approaches unity as long as this condition is met. And this gives you some sort of qualitative indication of the size of the measurement device. And this gives you an indication of the size of the system. This tells you how many photons are in the system, and this tells you how many photons are basically in the state that uses your phase reference to measure the other quantum state. And the only way that basically you want t to approach 1 such that because the probability of distinguishing the two is equal to 1 minus t. So if this condition is met, then you can reliably distinguish the two. And that is exactly what the authors want to show at the outset, which is namely to relate the size of the classical reference frame to the size of the superposition state itself. And here, this will probably be alpha squared, because I mean, the same condition, but this would be absolute value of alpha squared to be kind of precise. And so of course, if alpha is greater than n, then this condition is also met. But this is a kind of exact representation of this. So you can see that from this equation, probability of successfully distinguishing the macroscopic superposition from the incoherent mixture in a single measurement approaches unity as long as our classical measurement device is quadratically larger than the size of the macroscopic superposition. The authors also prove this for general macroscopic superpositions, but this is mathematically a lot more involved, and I think in the interest of time, I won't go through this. You should definitely read the paper if you want to understand this, this derivation in more detail, and there'll be also something on the forum. So here they consider this generalized large state, which isn't just a superposition of, say, two photon numbers. I think because we don't have that much time left, I think I'll actually immediately go to the discussion and maybe just want to illustrate future potential directions. So we've obviously only shown this for the photon superposition state, and you can repeat the same derivation for the total spin superposition state or the delocalized object state. You would just consider a different symmetry. So you would equivalently go through the same process, apply the G-twirling map, such that you represent your statistical mixture and your coherent superposition on a particularly convenient basis that it's easy to calculate the trace distance. And that gives you an indication of the success probability of your measurement. And yeah, the same result then can be shown for these two other types of superposition. And the authors, importantly, also show this for very generalized macroscopic superpositions. But I just want to quickly go to the end and maybe just say two more things. The first is that, of course, you can, we only consider a single measurement. And you can, of course, consider a repeated measurement. And all cases analyzed exhibited the same behavior for the probability of success. So this is another result that's shown in the paper that's pretty important, is that for a classical reference frame of size m, the trace distance between a superposition state of size n and the corresponding mixed state is generally given by this. Therefore, you require low t for high success probability, as shown here. So m must be larger than n squared. And this particular form is exactly, well, it's not the same, but it's quantitatively similar in its form to the one for the photon superposition state. And now if we consider not single shot measurements, but repeated measurements, in particular for a RF of size m, and if we repeat this particular measurement, we may want to wonder how many repetitions n, small n, would be required to witness a superposition and to distinguish it from the mixture. And this grows as a function of n. And then it should be noted that RF would also grow quadratically with n, and therefore, the trace distance decreases with n. So large superpositions can be certified without the need to increase the number of repetitions. But if the resources are limited, such that a quadratic growth of the reference frame is not possible, and in this case, the number of repetitions has to increase in order to compensate for the decreasing trace distance. And then by applying the Chernoff bound, one requires that n is greater than 2 log 1 over p exponent of n to the power of e divided by 8c. So e is epsilon, which gives you sort of the scaling behavior of the reference frame state RF. And this blows up exponentially with n, so this becomes an experiment that you can't really perform. It's practically, because this becomes so large, the number of repetitions becomes so large that this is practically extremely difficult to do. I think one of the last thing which is very fun to do is if you consider a model of a cat which consists of n spins in a superposition state, as we've shown before. We assume that each spin is represented by a water molecule. So for example, for a cat of mass 3 kilograms, and with a single water molecule having a mass of about 10 to the minus 26 kilograms, we have a cat of about 10 to the 26 spins, 10 to the 26 water molecules, each of which has a spin. And if we want to certify that such a cat is in the superposition state with one single measurement, then we would need to require a reference frame of size n squared, which is about 10 to the 52. And if we again consider this to be made of water molecules, then to distinguish between the statistical mixture and the coherent cat superposition state, we would need a reference frame, which is the size, which is 50 times heavier than the mass of the Earth. And this just serves to illustrate that this kind of experiment is practically completely infeasible, because you need to have some sort of reference state which is 50 times heavier than the mass of the entire Earth in your laboratory to perform this sort of measurement. It just serves as an illustration of the result itself. And yeah, for more details, I just really recommend looking at the original paper. Macroscopic superpositions require tremendous measurement devices. And thanks all for listening, and let me know if there are any questions.